Alrighty, so we're going to talk a little bit about waves. We're going to start with some definitions for waves. So basically, a wave is a disturbance that carries energy from one place to another. And, we see it like the up and down ripples in water. There's also waves that we don't see. We see the effects of them. There's light. We can hear the effects. There's sound. So waves are everywhere. Period is the time for one complete wave motion. So if you look at the little diagram there, the time it takes to go from crest to another crest would be the period. And the wavelength is the distance between identical wave parts. So once again, if you look at crest to crest, that's one wavelength. So it has to repeat itself. The velocity is the speed that the wave is moving, and the amplitude is how much it's displaced from the equilibrium position. We also have frequency, which is the number of waves that occur in a specific period of time. And that's commonly cycles per second, you'll hear, or hertz. So there's a specific equation we can use called the wave equation that helps us find velocity when we're given the frequency or wavelength of a wave. And the velocity of the wave is the wave's frequency times its wavelength. And the velocity is going to be in meters per second, the frequency is going to be in hertz, and the wavelength is going to be in meters. And here's an example of using that equation. You have an earthquake that produces waves with a frequency of 10 hertz. It takes 15 seconds for the waves to travel from the epicenter, where the earthquake started, to a nearby city 50 kilometers away. What is the wavelength of the wave? And so we have the frequency as 10 hertz. We're trying to find the wavelength. And we really don't know the velocity, but we know how to find it. If you think back to earlier lessons, velocity is distance over time. We know how far the wave traveled, that 50 kilometers. So we change that to 50 times 10 to the third meters. And we divide it by the time it took to travel, which is 15 seconds. So we end up with 3,333 meters per second is the speed of that earthquake wave. And we have the equation, velocity is frequency times wavelength, so we can use that to find the wavelength because now we have velocity and we were given frequency in the problem. So when you rearrange that equation by dividing both sides by frequency, you end up with wavelength is equal to velocity divided by frequency. Plug in the velocity that we just found and divide it by that frequency of 10 hertz, and we find that the wavelength of that wave is 333 meters. So it is a very, very large wave. There are basically two types of wave motion. There's transverse wave, and that's going to be kind of the wave we're used to thinking about, the up and down wave, where the displacement from equilibrium is perpendicular to the wave's motion. So if you look at the diagram that's on here, the wave is moving from left to right, but the displacement is up and down on the page. A longitudinal wave is a little different. There's no displacement perpendicular, it's all parallel. So you have to imagine that the longitudinal wave, which is instead of being up and down waves, it's a series of compressions and rarefactions or stretched out areas. So these sections of compressions travel the length of the wave, and that's what makes it longitudinal. Light is a transverse wave, and sound is a longitudinal wave. So what we hear as sound are actually those compressions and rarefactions. So when these traveling waves come together, and I've used pictures from transverse waves because they're a little bit easier to picture at first. When they come together and meet, they do something called superposition, and they interfere with each other, they interact. And when they do superpose, they create a new wave that's the sum of the two waves. So there's two kinds, basically. There's constructive interference, where the waves come together and they make a larger wave. The sum of the waves is larger. And then there's destructive interference, where those two waves come together and they cancel out, And the picture here is the extreme, where they completely make a wave that's the sum of the two maximum, so it's twice the size, or the destructive one where they completely cancel out into a nice flat no wave. And this is probably a more realistic example. The red wave and the green wave are the two waves that are interfering with each other. And you can see from the purple wave, which is the sum of the two, that sometimes that wave is greater than the two, and sometimes it falls in between where they've kind of canceled each other out a little bit. Any point along those waves, if you add the amplitude of the red and the amplitude of the green, you will get the amplitude of the purple. And in this case, negatives do matter, so you have to keep track of positive and negative above and below the x-axis. And then one special case of superposition is when the waves interfere and cause a standing wave to form. So these are waves that reflect back and forth between at least one barrier, sometimes two, and they form a wave that appears to not move, and that's why it's called a standing wave. So it just looks like a series of loops in front of you. And there's some specific vocabulary for a standing wave. So the antinode is the widest part where the amplitudes form the big part of the loop. I always think of it like you could stand an A up in there. Helps me remember. And the nodes are where there is zero amplitude or nothing. So that might help you keep track of what an antinode and a node is. Alrighty, there's your little bit about waves for today. Bye-bye.